The firecracker one. So, firecracker is dropped, and after falling a distance of this, explodes into two pieces of equal mass that are separated by an angle of this. All right. So, remember, in the Y's for these, you need some words, some explanation, but also a diagram of the momentums. So, really, in this problem, the momentums don't come into account until the explosion. So what's going on during the first half of this problem?
Firecrackers accelerating downward.
Firecrackers accelerating downward. We could describe that as a projectile or in free fall. You know, they mean the same thing, right? So we're doing the firecracker. So before explosion, it is accel down at 9.81 meters per second squared, right? What does it mean that it is dropped? What does that tell us? Anybody? What does it mean that it is dropped? Okay, so after it's dropped, it's in free fall. But what does it actually, the drops tell us? Okay, so after it's dropped, projectile, excellent. But what does the word dropped tell us? It starts, what is there? You're right. The initial velocity starts at 0, as opposed to being thrown down or thrown up or anything else, right? So, its velocity starts at 0. And then you have this explosion, right? What's true after the explosion? Okay, so we know what angle they go off at, right? But what must be true so that, and it's the reason they go off at that angle. It's something about the topic for this. Momentum is conserved. One kind of helpful hint is, if you read through one of your Y's for this section, and the words momentum is conserved are not in the Y, write them in the Y. Every one of these, the whole concept that we're working with is that momentum is conserved. So the momentum before the explosion is the same as the momentum directly after the explosion. Right? That's key to all of these. So now I need to do, so that's the kind of the written part of my Y. Now I need to do the vector part, and we'll do this side as before the explosion, and this one as after the explosion. Remember when we did the other ones, we had 3 boxes? We were looking at what was happening during the explosion. Here, let's look at just before and after as more general. So before, which direction is the firecracker moving before the explosion? And how many firecrackers are there before the explosion? 1. And which direction is it moving? Down. So we know that whatever direction the velocity is in, the momentum is also in. So it would have a momentum, and we'll call that, I don't know, momentum total maybe? And it's going to be downwards, because that's the direction of the velocity. How many things are there in the system, or how many pieces of the firecracker are there afterwards? 2. Now, there could be 3 or 4 or 20 million, right? But we'll keep it simple, and then we'll move on to the harder ones. Save those for the test, you know, the 20 million ones. So one is moving in that direction, and the other one's moving in that direction. Which one do you think takes away more momentum? Why do you think they're the same? Well, that means if I add up all the momentum afterwards, it's going to equal the momentum before. It doesn't mean everything has the same momentum. So you agree that they're going to take the same because they're of equal mass? Okay, so which piece is bigger? Well, let's see. I'm going to measure. It says 2 pieces of equal mass. But you're right. If there was a bigger one, maybe it would take away more, and it was moving faster, it would take away more momentum. But since they're of equal mass, I'm gonna assume that they take away the same. So I'm gonna actually just label each of these as P. Make life easier, because they take away each of them. Same amount, right? Now, the only other thing to be careful of over here in the half, if we write our equation, equals mv. Remember, it's a vector. So the magnitude of these aren't going to add up, but the vectors are, right? So in other words, if like p total is 10, does that mean each p is 5? No, because the direction matters. So they're not going to be 5. Think of them, the legs of a right triangle. We know the legs add up to the hypotenuse, but not 1 plus 1 type adding. The direction matters. So we need to break this down a little bit more. What do they actually want us to find? The speed of each piece. All right, so I'm going to break this into X and Y directions, because that's how I'm going to approach all of them. So beforehand, that's pretty easy. P total is all in the X direction. Afterwards, I've got P in that direction. Got some angle there. Oh, wait a minute. I know a little geometry. Let's see. If I've got something like that, and this angle is, for me, is what, 175? That's 175 degrees. And I draw that angle. Let's see. What would let's call this angle A, and then we'll call this one B. What would A plus 175 plus B equal? 180. Do you think it's okay to assume that A and B are the same size? Yeah, because these are taking away equal amounts of momentum, right? So that means A plus B equals 5. So A must equal 2.5. Yes? No? So that means in here I have an angle of 2.5 degrees. So this side is P, see, it's adjacent cosine, 2.5 degrees, and this side is P sine 2.5 degrees. I'll box it. This is what I did to figure out that mine was 2.5. Because since both pieces take away equal amounts of the momentum, there must be a symmetry there, so A must equal B. And then I also have P in this direction, where this is 2.5, and this would be P and good. So I've broken into components. So we know that the X components of the green have to add up to 0. How do I know that? X direction. Excellent. Yep, exactly. And the two Y components of the green need to add up to the blue because that's all in the Y direction. So I'm going to deal with, I think I'm going to start with the Y because I think the X is just going to tell me that those two are equal to each other. And while that's good to know, it's not, I don't think it's going to help me where I want to get to. So I'm going to work, I'm going to run out of room really quickly. I'm going to work in the Y direction. And so momentum before equals momentum after. So I've got, which direction you guys want to call positive, up or down? Down is a great choice because which direction does the blue arrow point? Which direction does the component of P vertically point? And the other one? So everything points down. Yay! Okay, I'm excited. So the momentum before, which is P total, equals the momentum after. P sine 2.5 degrees plus P sine 2.5 degrees. Well, are they both opposite the angle? Yep. So they're both sine. It's good to check that though, right? So let's see. Momentum total would be the mass total and whatever velocity it started with. I already took into account the direction, right, because of how I put them in. So I'm good there. This would be, P here would be half of the mass because it splits in half. Whatever velocity it has afterwards, sine of 2.5 degrees. Oh, I have another term identical to that, don't I? So couldn't I just multiply this whole term by 2? Because it tells me the firecracker breaks in half. No. Oh, so I shouldn't have the total here. I should just have it down. There we go. Anything cancel? Anything simplify?
If you multiply the 2 inside,
Oh, that gets rid of the half.
that gets rid of the half, and then it's divide both sides by half.
Well, yeah, I could do it then. I could do it before too, right? So, okay, so the m's are going to disappear, and the 2 times a half will make 1, which kind of disappeared. So the velocity before equals v prime, the velocity afterwards, times sine of 2.5 degrees. Do they tell me my velocity beforehand?
No.
No. Oh, I got to find that out though. Okay. Well, let's see. When it's dropped, I know it falls and accelerates for a certain distance. And if you think back to our equation sheet, we have the relationship that v final squared equals v initial squared plus 2a delta d. Back in like the top box of our equation sheet, I think it was. Maybe the second box. Okay, let's see how. So v final would be my v. My v initial Oh, I said it was dropped, so that's 0 plus 2. Now I said down. This should have a vector. Said down was positive, so my acceleration is 9.81 meters per second squared, and my displacement for mine was 1.44 meters. So let me see how fast my firecracker was going when it exploded. Let's see. No, this is my old one. My new one was the one that was stolen. Oh, sorry, borrowed but never returned.
I think you can move it back. I think you can move it to solar.
I think I can too. My detective service is still on the case though. I haven't gotten an update lately, but.
I forgot. My number is so much bigger than yours. I don't know if it's just because my degree is a lot bigger.
This has nothing to do with the degree. It has to do with how far it fell. Did you forget to square root it? I almost forgot to square root it. Most common mistake. Those nasty square roots. Why did math ever invent them? So that, oh, I shouldn't have boxed that. That's not a final answer. Sorry about that. Yeah, well, so that's how fast it's going before the explosion. That's my V. So if I want my V prime, all I gotta do is solve for it. And that's how fast each piece will be moving after the explosion. And I get 122 meters per second. Well, I have a very high angle. Mine almost head off at 90 degrees to each other. Let's see if I got it right. Alrighty. So we've got two cars hit at an intersection. Red car has this mass. And is traveling east with a certain speed, and a blue car of this mass is traveling north. The two cars collide and stick together. Hey, this is kind of like what you were doing in the interactive lab the other day with the red and the blue ball, isn't it? Two things moving at 90 degrees, and then they stick together. I wonder where I got the. I think it was arranged or something. Wow. So, what should I have in my Y? So many hands to pick from. Just blurt it out. Don't feel you have to read.
Momentum in a system is conserved.
Excellent. Momentum in a system is conserved. Always. Yay! And then let's do my diagram before and after. So red car is going east. Now, whoops. Now, should I draw that as traveling to the right or traveling to the left? If it says it's traveling east. Why to the right? Exactly, traveling to the east. So this would be the momentum of the red car ahead of time. And then my blue car is traveling north before they collide. So momentum of the blue beforehand. Which direction, just off the top of your head, do you think they're going to head, approximately? Kind of northeast-ish. And we'll call that something RB, because they're going to be joined together. All right? And what do they want to know? They want to know what's the speed of the combined cars and what direction does it move after it goes in north of east. So what I'm actually going to do is, because it's always conserved, I'm going to start off with a vector diagram, because by them being conserved, it means the red plus the blue has to equal the green. And that means that graphically, they form a right triangle. The direction is theta. The speed is going to be related to the magnitude of the green vector. So, see, what do I know? Well, I know an equation that says that momentum is inertia times velocity, right? What do I know about the red car before the collision? Mass and speed. So we know how the magnitude of the momentum, right? What do we know about the blue car before the collision? Its mass and speed, so we know its magnitude. So we actually know two sides of our right triangle. That's good, because that means we can find out everything. Remember, three things in a triangle, you can find anything, and I know three things. I know that this is the right angle, that's one. I know that side, that the red side is two. I know the blue side, that's three. So I'm pretty happy. So, let's see. What you want to find first? The hypotenuse or the angle theta? Let's go with the hypotenuse. Why not? So I know that Pythagoras relates the hypotenuse to the side, so that the momentum of RB squared has to equal momentum of the magnitude of the blue side plus the magnitude of the red side. So let's see, the magnitude of the hypotenuse would be the mass of RB times the speed of RB. The momentum of the blue side would be the mass of the blue, velocity of the speed of the blue. The red would be the mass of the red, the velocity of the red. This is just MB plus MR, right? I switched from uppercase R to from lowercase to uppercase. It should be consistent. It's Friday. Well, let's see. I know MB. I know MR. I want to know VRB, because that's the speed that they move off together. I know MB. I know VB. I know M. Oh, I know all those. So I can just, now it's just plugging numbers in, right? So now maybe I should move on to finding theta. I think I'm going to use opposite and the adjacent side because I know those sides, they give them to me. What trig function relates the angle to the opposite side opposite it and the side adjacent to it? Someone besides Adam. Tangent. Excellent. So the tangent of theta is going to be the blue side over the red side. So tan theta equals opposite TB over the adjacent PR. And I can always, oh, that's MR, VR, and that's MB, VB. Yeah, and then of course, right, I do the arctan of this, right? Yay! Yep, all I get,